Hi dear MECH 205 students. Well, under title Resultant of Distributed Load Systems, in the first record, well, mainly talk about the things to consider at this stage. How can reduce the distributed load system to a resultant force and a resultant couple moment. It is a common practice um, to give or to express the load, distributed load, as with the function of surface pressure. Instead of giving the load just in force unit, it is the common practice to express the load as surface pressure. The first video records, we perceive that, the volume under the load curve is equal to the magnitude of the resultant force of the distributed system. And at its special location, the resultant force can represent the rotation effect of the distributed load. And this location dimension is equal to the location dimension of the centroid of the volume of the space, which is under the load curve. However, the second part, this part, if the distribution, load distribution is a function of one of the axis only, but in the other axis, x-axis, along the x-axis, you see load is not uniform. But if along the other axis, in the other direction, the load is uniformly distributed, or in case, not uniform, but can be approximated as uniform distributed, especially if the dimension of the contact surface, which is the contact surface between the system and its surroundings, is very small relative to the size of the other dimension of the contact surface, then the say distribution in the direction where the size of the contact area is very small, very accurately as if uniform. Either it is expressed that uniform, or we can assume that it is uniform, while the variation is negligible because the dimension is very small relative to the other dimension. Okay, in such a case, if the load is a function of only one coordinate value, the other direction is uniform, but it is the common practice. We multiply the surface pressure, it is the given load function, by the dimension of the contact surface, okay, in the direction of that dimension, the distribution is uniform, or can be very accurately assumed as uniform. Okay, multiplying the pressure, surface pressure, with that dimension can obtain a new load function. It is denoted in the book written by Hibeler with lowercase w. It is going to be again the function of x. Okay. Such a special case, yeah, yes. Well, the load curve is not per area, newtons per meter squared in pressure unit Pascal, but newtons per unit of distance, unit of length, newtons per meter. And in such a case, the magnitude of the resultant force will be equal to not the volume under the load curve, but the area under the load curve. Let's prove that it is so. Well, for instance, over the contact surface, take such a part. It is with this infinitesimal small dx. In this example, we have x coordinate axis. It is extending along the length of the object. It may be a shaft or it may be a beam, something like that. Okay, well, over the contact surface, we selected a infinitesimal small segment. It is with this dx. If we multiply the length of this width of this segment and the value of the load at that place, since it is infinitesimal small, practically can say that at this point. Okay, if you multiply the load function, okay, by the width of the segment, it is going to be the magnitude of the corresponding force. Here, at that point, well, due to the existence of distributed load, we have such an infinitesimal small force. Okay, its magnitude is equal to the value of the load at this point times the width of this contact surface, the width of the selected segment over the contact surface. Well, W times dx is the area of the rectangle. It finds its place at that point under the load curve. Okay, this is one of the areas under the load curve. Well, infinitesimal small area. Well, we have under the load curve infinite number of infinitesimal small areas. If we add them up, then the result will be the total area under the curve. But since each area corresponds to the magnitude of the corresponding force that is applied by the surroundings onto the system due to the existence of such a load, can say that the integral of this integrand from the beginning of the distribution to its end, in the example from 0 to L, is equal to the resultant of the distributed load system, magnitude of the resultant of the distributed system. But since W times dx is the value of the area under this part of the curve, this is also equal to the total area under the curve. Okay, in short, this means to be able to find the resultant magnitude of the resultant force, the thing to do is that just simply be able to calculate the area of the space which is under the load curve. Well, this area is a special area. One dimension, it is well in the distance unit, but the other dimension, it is force unit per length. Okay, so the area corresponds to the magnitude of the resultant force, and its unit is Newton in SI unit system. Well, at the intermediate stage, well, mind, that is the consideration. At point O, we have the resultant force of the distributed system, and well, it is at point O to apply. If we apply such a resultant force at point O, considering the rotation effect of the given force system with respect to point O, then well, the given system and that new system will be equivalent. Well, if we consider the rotation effect of each of the elements of this distributed load system with respect to point O, we obtain a resultant moment couple. Okay, M resultant couple. Okay, this is the couple. It represents the rotation effects of the forces in the given load system, force system. Okay, but we know whenever the line of action of the resultant force and the resultant couple moment are perpendicular to each other, 90 degrees, angle is 90 degrees, then, well, this system can furtherly be reduced a new system, and this system can be replaced with a new one, where we have only one vector. It is the resultant force vector. Well, it is at a special location. Okay, it is x bar millimeters away. The line of action is x bar millimeters or meters away from the reference point. At this special location, it can represent not only the translation effect, but also the rotation effect of the distributed force system, of the given force system. Well, to be able to find the coordinate for the line of action of the resultant force, the equation to satisfy is that the resultant moment couple must be equal to the moment of the resultant force at its special location. In other words, the moment of this resultant force must be equal to the resultant moment couple. That is the governing equation. Okay, well, write it. X bar times F resultant, magnitude of the resulting force, must be equal to the moment of the constitutive forces of the system. For one of the forces in the system, magnitude is dF, and its moment is x times dF. Okay. Now, in the example, this moment is negative. Because this force dF tends to rotate the object in the clockwise direction. And the resultant force must have the same rotation effect. So you see at this special place, it tends to rotate the object about point O in the clockwise direction. So its moment is negative. Okay, this term is one of the moments of the forces. Well, how about the moments of the others? Well, just take the integral. Now, this is equal to that one. Well, sum of the moments of all the constitutive forces, x times dF is the moment of one of the forces. Well, if we add the moments up, we obtain this term. This term is the magnitude is equal to the magnitude of the resultant couple. Yes, this resultant couple moment must be equal to the moment of the resultant force at its new location. Here, the only unknown in this equation is the coordinate value. Solve this equation and find it. Now here, well, this expression, well, is, x times df. df is equal to dA. Okay, x bar is equal to integral of x dA divided by F resultant. F resultant is the total area under the load curve. From here we know that it is so. So well, this expression, dear students, exactly the same to use, okay, as to use for finding the coordinate of the centroid, center of the area. Which area? It is the area under the load curve, this area. Okay, it is the same expression. So from this analysis and interpretation can conclude that the representative resultant force at its special location passes through the centroid of the area under the load curve, while the coordinate of the centroid of the area under the load curve is also the coordinate of the line of action, the coordinate for the line of action of the resultant force. Okay, if we know the centroid of the area under the load curve, then this means we also know the location dimension of for the line of action of the resultant force. Okay, doing such things, then we'll study on some examples. Well, before the example, yes, the same things are given on this slide. The resultant force, okay, or the distributed load system is equal to the total area under the load curve. Prove it. Well, for proving purpose, well, select an infinitesimally small part of the contact surface. Its width is dx. dx times height is the area of the rectangle which is under that part of the load curve. Load curve, the value of the load curve at this point times the width of the contact surface is the area of this rectangle. If we add these rectangles up, we have infinite number of rectangles under the load curve, then we obtain the total area. Well, since W times dx is df and integral of df is the resultant of the distributed load, this means resultant force is equal to the area under the load curve. And then this expression is the moment equality. The integral of x df is the magnitude of the resultant couple moment. It must be equal to the moment of the resultant force at its special location. In this equation, the unknown is x bar. Okay, x bar is equal to the expression that is the same expression it is used for finding the coordinate of the centroid of the area under the load curve. Okay. Yes, this expression is exactly the same expression. Okay, well, if we know the centroid of the area, then we can say that, okay, resultant force is passing through that point. If it is over there, then it can represent the effect of the distributed load, not only to translational effect but also rotation effect. Yes, well, here there is is a summary in this window, important points to pay attention to know. Already talked about such things. Okay, an example. In the example, well, the load curve has been given as 60x squared. Well, the load is a function of x. Well, there is a shaft in the example. Yeah, it is written shaft. Well, at the left-hand side end of the shaft, the load is 0. At the other end, reaches to maximum value. The unit of the value, well, if we substitute the value of x for this point into the load function, 2 is the coordinate value, x value for this point, 2 times 2, the square of 2, 4, 4 times 60, it makes 240 newtons meter. Okay, the maximum value of the load curve finds its place at this end of the shaft. Okay, the area under this load curve is the magnitude of the resultant force. Okay, then calculate it. For one of the strips under the load curve, dx times W is the area. If we add such areas up, taking the integral, we find the total area. Okay, load value of the load curve at this point is the height of this triangle, rectangle, times it is width, dx means. Okay, and take this integral from 0 to 2. The result is the total area under the curve, and also it corresponds to the resultant, magnitude of the resultant of the distributed load. It is 160 newtons. Okay. And then, well, if we shift the force, resultant force, to that special location at which the rotation effect of this resultant force will be equal to the rotation effect of the distributed load, then it can represent the effect of the distributed load system fully to both, to the translation effect and the rotational effect. Okay, the coordinates of for the line of action of the resultant force, you see, can be determined using the expression. It is exactly used for finding the coordinate of the center of the area under the curve. In our example, we know the load function. Okay, load function times dx corresponds to the magnitude of the force at the point. Well, it is moment length is x. Okay, and if we add the moments of all up, we obtain the magnitude of the resultant moment couple divided by the magnitude of the resultant force. It is the total area, is the coordinate value for the line of action, and it is the coordinate of the centroid as well. In the example, it is 1.5 meters. Okay, another example. Well, in this example, the load function is surface pressure given in terms of pressure, but since in the direction where the dimension of the contact surface is 0.2 meters in the y direction, distribution is uniform. So while multiplying the pressure with the dimension 0.2, we obtain what? We obtain the function of the load curve not in pressure unit, but unit of force per length, newtons per meter. Okay, the load function, well, here in the end, 160x newtons per meter. Okay, and then in this figure, figure B, what we have, distribution is linearly increasing. Well, the area under the load curve is a triangle. Okay, well, at this point, the end of the beam, it has been fixedly connected to a fixed frame. Well, the load curve reached the maximum value. Well, 160, substitute the value of x, it is 9. 9 times 160, the value is 1440 meters per meter. Okay. If we can calculate the area of this triangle, this means we found the magnitude of the resultant force. Then from elementary school, everybody knows the area of a triangle is can be calculated multiplying the width of the triangle to its height and taking the half of the result. 1 divided by 2 times 9 times 1440 is the total area of the triangle, and physically to its meaning corresponds to the magnitude of the resultant force. Okay. And then yes, well, if we locate the resultant force not at point O, this point, but at a special location, well, single resultant force well represents the translation effect and also the rotation effect of the distributed loads system. Okay, the moment of the resultant force at such a special location must be equal to the resultant couple moment. We know the line of action of the resultant force at such a special location passes through what the centroid of the area under the load curve. For a triangle centroid, we know that uses the coordinate value. It is equal to a third of the width of the triangle. The width of the triangle is 9 meters. A third of it is 3 meters. This one. But if the location dimension is to express not relative to this end, but relative to the other end where we have the origin, okay, then well, total length minus a third of the length of the width of the triangle, it makes 6 meters. That is the coordinate for the line of action of the force. Now this single force at this special location is exactly equal to the given distributed load system to its effect. But of course, such an equivalency is valid if the object is a rigid body. We know, say, rigid body mechanics, we assume the material as rigid. Neglect the deformations, neglect the effect of the deformations. So if the body can be assumed as rigid body, then yes, we can say replace such a complex force system with a single resultant force at such a special location. Okay, another example. In this example, yeah, well, the area under the load curve is a trapezoid. Why not? Trapezoidal area can be considered as a composite area and subdivided into rectangular and triangular areas. And then knowing that the area under the load curve is equal to the magnitude of the resultant of the distributed load. Well, for triangle, corresponding resultant is F1. For the rectangular part of the area under the load curve corresponds to the magnitude of the resultant force. It corresponds to the rectangular area. The line of action of F1 passes through the centroid of the triangle. Line of action of F2 passes through the centroid of the rectangle. Okay, x1 is the coordinate for the center of the triangle. It is a third of the width of the triangle. The width of the triangle is 9 feet. A third of it is 3 feet. For a rectangle, the centroid, coordinate of the centroid is equal to the half of the width of the rectangle. It is 4.5. Okay, well, if we calculate the area of the rectangle and area of the triangle, yes, these are the values. Okay, F1 is the resultant. It corresponds to the area of the triangular portion. It is 225 pound force. F2 is the force corresponds to the resultant of the distributed load. It corresponds to the rectangular part of the area. It is 450 pounds. And yes, the coordinates for the line of action of F1 and F2 are over there. And then, yes, the resultant of the distributed load, obvious, the sum of resultant of F1 and F2. F1 plus F2 is F resultant. Well, the moment of F1 plus moment of F2, is the magnitude of the resultant moment couple of this distributed load, and the moment of the resultant force at that special location, it is coordinate is x bar, must be equal to the resultant moment couple. Okay, writing that equality, here it is, can find the governing equation. Over there, the only unknown is x bar. Solve this equation and find the coordinate value. Yes, dear students, the second part of the record under title The Resultant of Distributed Loads, talk about a special case with the associated examples. In the case where the load curve is not surface pressure but in the unit of newtons per meter, or in British American unit system, pound force per feet. If the distribution distributed load is a function of only one variable, in the other direction it is uniform, just the common practice is that multiply surface pressure by the dimension of the contact surface in the direction the distribution is uniform. We obtain a new load curve. It is not in the unit of pressure, but it is distributed load newtons per meter. Okay, ending the second part of my lecture notes. Okay, thank you for your interest, dear students. Bye bye.